14 days. That is how long it took me to configure, build, and successfully deploy VyOS to our development board, and not one single step of this journey was a smooth one. In fact, pretty much every problem I encountered along the way took me at least 2 to 3 days to solve, almost as if the universe simply didn't want me to succeed. But alas, I emerged victorious. And surprisingly, none of the issues I had to solve were VyOS's fault, at least not directly. Let me explain. In my previous video, I shared my concerns regarding the operating system that we want to choose as the one that we will ship our router with, and a bunch of you have suggested for me to look at the VyOS. A bunch large enough that I thought to myself, you know what? Challenge accepted. But then that challenge turned into a nightmare. Each and every single step of the way introduced a new problem that felt like I've done 2 steps backwards. Let's take the kernel as an example. Well, not as an example. It was indeed the first major step towards building an OS image for our board. You see, VyOS already provides a kernel configuration that's tested and proven to work. But that kernel, unfortunately, doesn't come with drivers that are needed on our board for all its peripherals to run correctly or at all. So I was faced with the following problem. How do I take the kernel and its configuration that's provided by NXP, the makers of our CPU, and merge it with the one that's provided by VyOS? Now, keep in mind that a kernel configuration file can have tens of thousands of options, so comparing 2 of these isn't exactly as straightforward as you might think. However, luckily for me, kernel does come with a couple of scripts that make it somewhat easier for us to compare 2 different configurations. And the tool I'm talking about here is called diffconfig, and it does exactly what it says on the tin. It prints out the differences between 2 separate kernel configurations. Now, if the amount of differences is fairly small, then you can take the list and just go through each and every item by hand and decide whether you want to turn it off or on, so to speak. But to my misfortune, the amount of differences in my case was like several thousands of them, so a one-by-one approach wasn't really an option. Instead, what I did is I googled around for a script that would let me merge 2 configurations my way. And luckily, I quickly found one which was, best of all, written in Ruby, a language that I'm quite proficient in. And in order to understand this script, let's have a quick look into it because it's actually quite simple. It only needs to handle 3 possible types of changes when comparing 2 kernel configs. The first type of change starts with a minus, which means that the second kernel config didn't have this item configured, but the first did. The second type of change is where both configs actually configured the same item but differently. As you can see here, the diffconfig output actually makes it very clear whether a line changed between 3 possible values, y, m, and n, which translates to yes, as in this item will be compiled into the kernel, m, as in this item will be compiled as a separate module, and finally n, as in, you guessed it, no, this item will not be compiled. So if we go back to our Ruby script, this part was actually the most challenging and I had to modify it in order to satisfy my own requirements. 1. If any of the configs says yes to an item, then it stays yes. And 2. If any of the items says module but the other says no, then it stays a module. And finally, I also needed to inverse the logic for the lines that start with minus, because the script wanted to remove them from the final config, whereas I wanted to keep them in. With these changes applied, I finally ran the script and built the kernel. Or did I? Well, I did not, because the darn thing wouldn't build successfully. And for those of you who have never compiled the kernel before, it can take a long time, hours even. You could say I'm lucky in that regard because I'm compiling inside a virtual machine on my M1 Mac with 64 gigs of RAM, which speeds up the process significantly, because they're both ARM64 instruction sets and no translation is needed. This approach got me down to only 10 minutes or so per run. So why didn't it build? Well, if I tried to build the kernel that came with VyOS, it built without issues. And if I tried to build the one that came with the board, well, that one also built without issues, so it was a combination of the two that didn't. So how do you find a problematic item in a config file that's several thousand lines long? Well, you divide and conquer. Literally. I took the diff-config file that I was merging with my Ruby script, removed first half, ran it again, and if it built, the issue was in the half that I removed. But if it didn't build, it was in the half that I didn't remove. See where this is going? This method is called a binary search, and in my case it took around 15 tries in order to find the offensive line called config fortify source. I don't know what it does. I don't care. 15 tries of building the kernel still means 15 times 10 minutes for each run, and I just didn't want to spend more time on this. Instead, now that the kernel was finally compiled, I went back to the VyOS build script and ran it with this new kernel now in place for it to do so successfully, right? No, of course not, because that would be way too easy. And you know what the issue was? Two kernels were plugged into the operating system image that VyOS builder was, well, building. Why? Because I wasn't paying attention to the documentation. You see, it does say that in order to provide a custom kernel, which you can totally do, you also have to build a couple of separate packages that are compiled with that specific version of kernel. Otherwise, VyOS will provide these separate packages, which in turn will require the kernel with the version that they were compiled for. So, because I wasn't paying attention, I ended up with two kernels in the image, building of which would fail because some script got confused as to which kernel they should work on. Now, with this particular problem, Debian already comes with a program called Y. So, I was able to go into the image that was not built successfully, find the kernel that I didn't want, and ran Y on it. If you never used it, I don't blame you, neither have I, but this Y gives you the answer as to why a particular program was installed on the system. Or to put it differently, who or what requested it to be there. It's a dependency of another program. And in my case, that program is called Joule, which I have no idea what it does, but at that point I did remember I saw a script called build Joule in the same folder that the kernel config scripts were. So I went back to that folder, ran the build Joule script, and this time also had a more careful look at the documentation, which does indeed say that in order to provide a custom kernel, you also need to build a couple of other packages. So I did exactly that and finally succeeded in building a custom VyOS image. So then I took that image, flashed a USB thumb drive with it, and installed it, right? Ha! I wish. You see, there's an issue with VyOS that's responsible for 90% of my problems going forward, and that is the fact that it needs UEFI. For those of you who don't know what UEFI is, when you turn on your computer, you often first encounter a post screen that says you can press F2 to get into the BIOS. Well, technically that's UEFI, but we call it BIOS primarily for historical reasons. Anyway, the bootloader of choice for VyOS is Grub. And in case you don't know, Grub is that interface that sometimes asks you which operating system or mode you want to boot into. And Grub needs UEFI. UEFI. And don't get me wrong, I'm not blaming VyOS team for this. I actually commend them for this choice. Instead of building yet another custom built system that nobody understands, they decided to take one of the most common and stable Linux distros out there, Debian, and use its live build system, part of which is also Grub, which in turn relies on the UEFI. Now, despite my particular use case and its issues, using a well-established build system also means there's plenty of documentations and ways one can modify this build to behave exactly like they want it to, so good choice, VyOS team, and I mean that. You see, the default bootloader that the development board that we use ships with is called U-boot. This U-boot is technically the third piece of code that is ran after the CPU is powered on. The first piece of code is actually inside the ROM within the CPU that's responsible for it to correctly communicate with the second piece of code, also called the first stage bootloader. This stage is responsible for initializing RAM because the next piece of code, so the second stage bootloader, also contains U-boot, and that U-boot needs to upload itself into RAM in order to be able to run. And when it does, it's also the first environment we can actually interact with. And it's here when you can enter the necessary instructions to boot the operating system. But before we get there, let's actually discuss the 3 mandatory components to run an embedded Linux system and one optional one. First, since we already spoke about it, we need a working kernel. Think of it as the brain of the system. Then we need a device tree, which in a nutshell is a very simple file that describes how all the components of the system are wired together, because unlike your regular PC, embedded devices for the most part don't have something called ACPI. Without going too much into details, kernel needs something to tell it how external devices are connected to the CPU, and in the PC world, that something is the ACPI protocol. But in the embedded world, those are device trees. And for our board, a number of them is provided by the manufacturer already, so there was literally nothing for me to do here, since they also get compiled alongside with the kernel, which then also needs the third mandatory component, and that is the root file system. Actually, I'll mention the fourth optional component here as well, and that's the initial RAM disk that also holds the root file system. This means that you only need one of them, but you can have both at the same time as well. The only difference being that your normal root file system lives on some sort of a storage medium, be it an SSD, an SD card, or a NOR flash chip, whereas the initial RAM disk lives, as the name suggests, in the memory. If you ever installed Linux, then you've seen a RAM disk in action, because Linux installers use this RAM disk to run all kinds of scripts during the installation, while the actual hard drive has no operating system on it yet. But some systems, like VyOS for example, take this even a step further and load the file system into RAM every time and run it from there, and just mount the actual hard drive only in places where changes need to be saved permanently, such as the /etc directory. This episode is brought to you by PCBWay. I've been working with them on my custom keyboard project, and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. Okay, before moving on, let's repeat. For Linux to run successfully on an embedded device, you need the kernel, a device tree, and either a permanent root file system or a temporary RAM disk. And this is exactly how U-boot expects us to boot into Linux. It has a command called booti, which expects 3 parameters, so kernel, initial RAM disk, and device tree, all of which we need to preload into memory and then give those RAM addresses as 3 arguments to that booti command. But that command boots directly into Linux, which means there's no UEFI in the stack. And well, VyOS doesn't like that, because when you try to install it permanently, it will fail as it can't access it. Now, luckily for us, U-boot also ships with something called an FE stub. If you're not familiar with the term, stub in software development means a fake, a replacement. One that's just good enough that it fools the systems that use it into believing they're talking with the real thing. And unlike booti command, bootEFI command only needs 2 parameters. The EFI binary, which in our case is built by VyOS Builder, and it includes both the grub and device tree. We don't need to pass kernel or initial RAM disk here, because these 2 components get loaded by it rather than U-boot. And here's where I stumbled upon one of those problems that take a disproportionate amount of time to solve, but are caused by a fairly minor thing that in hindsight is so trivial that, well, you'd never think it was an issue in the first place. You see, whenever I tried running the bootEFI command, the whole board crashed, regardless of how the EFI binary that I passed to it was built or what device tree I gave it. It simply kept crashing and crashing and crashing until 3 days in, I finally found the answer in the U-boot mailing list archive. And you know what it was? An environment variable that was implicitly taken into account when booting into UEFI. which means that all I literally had to do was simply to remove it, and then the system would boot into EFI/grub, which in turn would get me to the VyOS live image/installer. And from here on out, things went as smoothly as one would hope. You didn't believe what I just said, did you? Because it's not true, but luckily for me, the final issue I needed to fix wasn't as major as all the ones before it. The thing is, when you do a permanent install of VyOS, it also needs to update grub, which in turn needs to update the EUFI boot order. But since we're using a stub EFI, that stub doesn't expose itself to the operating system as writable, which breaks the installation. You see, traditional full-fledged UEFI has access to an NVRAM, into which it stores all the configuration, but in the embedded world, we don't have that luxury. However, luckily for me, U-boot does come with an option to configure the EFI stub to write to the regular RAM, which in turn exposes itself to the operating system as writable, so that grub can then save the correct boot order setting. But Tomasz, won't that boot order then get discarded at system reset because it's not permanently saved? Yes, it will. But that's not a big issue because we can always either manually add it to grub or write a script that will do it for us. In any case, it's a problem that's easily solvable, and that doesn't impact my ability to test VyOS on our board thoroughly. But that is not to say I actually succeeded in that, at least not yet. And the reason for this unfortunately lies outside my skill set, which is why I reached out to NXP's technical support, and they're now helping me solve this issue. Remember the kernel that they provide for their CPUs that I mentioned earlier? Well, they offer two variants, one that provides upstream drivers and one that provides quote-unquote private drivers. The former ones are merged to the mainline Linux kernel, while the latter are developed directly into the NXP's kernel and are highly optimized for their chips. And unfortunately, I couldn't get those private drivers to boot through UEFI, which is why the interfaces, network interfaces that is, simply error out on boot and are then not even available or visible to the operating system. Absolutely no idea what's wrong here, because if I boot them from U-boot directly bypassing UEFI, they work just fine. But then parts of the VyOS don't work correctly. At any rate, go ahead and click that subscribe button because, as I said, I'm working on this issue along with the NXP technical support, and I'm hoping it'll get resolved by when the next month's update video comes out. And in the meanwhile, I'll configure VyOS using the regular upstream drivers because those work just fine and I can normally use VyOS. It's just that the networking stack isn't living up to its full potential. Now, before we move on, I need to thank all of you for suggesting it, and here's why. My ultimate vision is to have a user interface that is both amazing to use and easy to understand. And for my previous video, I prepared a simple file system that's based on a lot of similar packages that VyOS also brings to the table, with the addition of being a well-known and proven routing solution based on Linux. So thank you, keep commenting on my videos with great ideas, because this is not a me project, it's an us project, and I appreciate all of you for being part of this story. Okay, if you're still here, thank you. May I ask politely to click that like button, because it really helps the channel out. The more people see my videos, the bigger the pool of great ideas going forward. And since we're talking about ideas, we also had one that's a bit more expensive, and that's the fact that we realized that the layout process will take anywhere between around 300 and 400 hours. In case you don't know, layout is where you take a PCB schematic and turn it into a PCB so that you have all the components, of which we have around 1500 if you remember from my previous video, and place them on the PCB. It might sound easy, but it's a very involved and intricate process, as components can have anywhere from 2 connections, think resistors and capacitors, and all the way up to almost 800 of them, which is our CPU. And each and every of those connections needs to, well, connect 2 or more components, which is why one of the first decisions to make is the number of copper layers that the PCB is made out of, and that is called a stack up. Given the small size of the PCB and the fact that we have 10 gigabit connections on it, we will likely end up with 10, 12 or maybe even more layers, but since we literally just started with the layout, that decision has not been made yet. Oh, and one more decision we made in the past month that is worth mentioning. We're not going to stick to the Nano ITX standard we've initially planned to, because, well, apparently it's not even a standard, but more of a set of guidelines, if you will, if even that. In fact, we reached out to VIA, the company that's responsible for ATX, Mini ITX and all other motherboard sizes that we know and use today, and they, somewhat expectedly, didn't even respond, which led us to do more research on the topic. And the result? Well, based on our findings, it's a bit of a wild west out there. The only three things that most boards have in common are the sizes of the boards, positions of the mounting holes, and finally the I/O being positioned in a way that's compatible where computer cases have the I/O shield. So, while we decided to stick with 12 by 12 centimeter board, we also decided we will prioritize form over function when it comes to connectors, given we don't aim for our board to be installed in a PC case, and function over form when it comes to mounting holes, because if we just put them on the corners of the PCB, then we risk it bending slightly against where we plan to use the thermal rubber pads to increase the thermal performance of the case itself. Does that mean that there will be no standard case for our PCB to fit into? Yes, but given that each router manufacturer also does this, we don't see it as a big issue, especially because we plan to publish the step file of the board so that the more creative ones among you can also have a go at the case design. So what's so expensive about what I just said? Well, given the amount of hours needed for the PCB layout and our goal to start producing the first prototypes sometime early October, we decided to hire a professional layouter, which is someone that does this for a living pretty much. This will set us back around $10,000 or so, but will also move the timeline backwards a month, and given we're in a good financial position with the current burn rate, I'm not particularly worried about this somewhat unforeseen expense. Overall, I'm quite happy with the progress, considering we've started with the development of the router like 4 or 5 months ago, and we're expecting the first prototypes to be ready by October. But before we get there, I'm also thinking of making a Q&A video, so if you have any questions, concerns or suggestions, write them down in the comments below, and those that get the most votes will get addressed in that video. But for now, Tomasz from Slovenia, signing out.